Thanks, Christo. That's for that very, very charitable introduction. There's been a title change, but I assure you the content didn't change. It's just that I prepared my slides and tried to cluster my talk into themes, and I couldn't come up with 5 themes, so I changed the title. But here's the thesis of what I want to tell you about. The thesis is that in the last 25 years, essentially during my career as a computer scientist, computing cycles have migrated from doing work in mainly scientific computing and for the enterprise to a world where most computing is done for consumers. And what this has done to us is it's transformed the way computing cycles are consumed, and it begs us to look at consumer behavior when we think about algorithm design and computing. And so the theme that I'll strike today is really how does consumer behavior change our thinking about algorithm design. And at the end, I'll intone how this demands a deeper interaction between the techniques and tools we used to in mathematics and computer science and the social sciences, which is a field that's largely, outside of microeconomics in a few areas, largely been untouched by the kind of heavy mathematics that we bring to bear here. Okay. I was told at dinner last night that there were no controversies at the symposium, so I'm going to try and make these wild claims and hope that somebody finds it controversial. Some of this, this end state that I'll talk about really should echo some of the themes that John Kleinberger would have talked about on Wednesday. All right, to set the stage, I'm going to begin with a small warm-up exercise. So this is a simple algorithm I'm going to tell you about, but it really is one where something fairly standard is dramatically aided by our understanding of human behavior. Okay? And the setting is that of a connectivity server, which is a beast that you find in all the internet companies, right? So you have this thing called the web graph. So to give you a sense, a web graph is a graph whose nodes are the pages on the web. To a very rough order, think of the number being 10 to the 11 or 10 to the 12. Okay? The average degree is of the order of 10. Okay? So that's the size of the beast you're dealing with. Okay? And the question that we want to provide support for is what I'll call adjacency queries. So I give you a node, and I ask you who are the neighbors. Okay? And this has rich applications all over the internet industry, and certainly the web search industry. Okay? And what I'm going to do is, in the next 5 minutes, show you a simple scheme for doing this that, by a metric that I'll point out, does it dramatically better than the obvious. Okay? And it really does hinge on our understanding of consumer behavior. Okay? All right, so let's say each URL is represented by an integer. And for the purposes of a running example, think of only 4 billion pages on the web, although I did tell you a moment ago that it's really about 20 or 30 times that number. Okay? But that gives you a nice round 32 bits per node. Okay? So to represent an edge, to write down an edge that goes from A to B, would, in the simplistic way, take you 64 bits. Okay? All right. So what I'll show you is a scheme that achieves about 3 bits per edge, and it's a really simple scheme. Okay? So that represents a dramatic, almost 2 orders of magnitude savings on the obvious. And what this really hinges on is understanding how content is created on the web. Okay? And some people at Microsoft Research took the work that I'm about to describe and squeezed the bits down some more, getting down to about 2 bits per edge. So you know, the facetious way of looking at it, which is the title of the paper I wanted to write, except I didn't get the result, and the guys at MSR did, that the web is a 2-bit graph, really, right? But the thing you should think about is if you can really write down the web with about 2 bits an edge, that's the degree of randomness that exists in the web. It's a very, very non-random graph. Okay? All right, so what's the main idea, right? So there's a bunch of ideas exploited in the compression, and before I embark on this, I want to stress that not only do we want to squeeze the web graph down so it fits in main memory, we also want to provide support for queries. So it's not just a matter of running gzip or your favorite compression algorithm. Okay? And the scheme that I'll describe will, in fact, accomplish that. Okay? So we'll make use of the similarity between lists. Okay? We'll make use of locality in a certain sense that I'll talk about. And then some heavy-duty coding theory that exploits the particular distributional properties of certain integers we see. Of these 4 aspects, the last 2 I won't really talk about. They're relatively standard coding theory. The first two are where the idea here lies. Okay? Okay. So these ideas are due to Paolo Boldi and Sebastiano Vigna. And here's the basic idea. You take all the URLs in the world and order them lexicographically from top to bottom. So you start at adam.com or whatever and go to zoology.org, right? And everything in between. And you just order them lexicographically, and nothing fancier than that. That's all there is to it. Okay? And the key observation that Boldi and Vigna use is one of similarity in this ordering. Okay? So what's the idea? The observation is that because of templating, because of the way people expect to consume web pages, because of the way people create web pages, it turns out that the adjacency list of every node is very similar, most of the time, to one of 7 preceding adjacency lists. The constant 7 is not particularly important other than it's optimized in practice. What's important is it can be written down in 3 bits. It could be 15, 31, et cetera. But in this lexicographic ordering, it takes very little space to express yourself as similar to some recent URL. Okay? So let's take an example here. If you consider the 3 white adjacency lists, okay? So now I've replaced all URLs by integer identifiers. Okay? And I'm going to look at the last one, the blue one, which I hope you can see. It's a bit dark. Okay? The observation here is I'm going to encode the blue adjacency list as follows. I say, look at 2 adjacency lists ago, that's -2, and simply replace the 9 by an 8. Okay? All right, so what have we done here? We've used about 3 bits to say how far back to look. Okay? And then we've written a little local rewriting to get my adjacency list. Okay? And the claim is most of the time this will work. Most of the time you can very succinctly write down an adjacency list in this form. Okay? And if you do this right and do all the right coding that goes with it, it takes you about 3 bits to write down an edge. Okay? All right. So what have we done here? Right? So you depend heavily on this canonical ordering. Now, nobody asked the question, why 7 and not 8 if I give you 3 bits? Okay? And the reason is that every now and then you get out of stanford.edu to a new domain, and you don't have anybody in recent history to write yourself in terms of, so you just start anew. Okay? All right. So what's going on here is that because of the behavior of page creators, because of the way humans behave, we're able to exploit similarity in this canonical ordering. Moreover, this is done in a way that adjacency queries can be answered pretty efficiently. In order to reconstruct an adjacency list, all I need to do is look at this encoding. So it'll point me back somewhere and say, well, look 3 spaces back. And that might say, look 5 spaces back. And we may have a chain of this sort. In principle, it could get pretty bad. Okay? In practice, it never gets bad. It never crosses 4 or 5 hops. Okay? That is begging for some nice theory to explain it. Okay? But here's an instance where you not only get the compression, you also get these very short chains that result. Okay? All right. What's also nice is that encoding is a simple one-pass algorithm once you've done the sort. Okay. So that was a quick warm-up exercise. And what I'm going to do for the remainder of my time is strike 3 themes around how consumer behavior is actually affecting what we compute and how. And the 3 themes, I'll call them subjective functions in contrast to the objective functions we're always dealing with in our business. I'll talk a little bit about data distributions that arise from consumer behavior and how we should address these. And finally, I'll recall the time, Christos mentioned I was a student here. Back when I was a student, PRAMs were all the rage. Certainly, I see many colleagues from that era who we all worked on PRAMs. That's not quite how the world turned out. And I'll talk a little bit about how parallelism works and the different challenges, algorithmic and theoretical challenges that parallelism today demands of us. Okay. So as I promised, the thesis here is the bulk and growing fraction of computational resources today are driven by consumers. Okay? There's still, of course, lots and lots of cycles expended on things like sort and select, so database operations and sorting and so on. But a growing chunk is expended on this nebulous thing, and you'll see in a moment how nebulous it gets. That's called, we need to make users happy, okay? And when you teach this stuff, one of the things you find is you're always in this business of saying, well, what we really after is user happiness, but here's this proxy that we're going to compute instead, and we're going to optimize this carefully, and we put a lot of effort into it, and you'll see a couple of simple examples in a moment. But really, this elusive thing we're after is user happiness, right? So in a sense, you have 7 billion different so-called objective functions, except nobody can write them down. And yet, we're always computing and optimizing proxies for user happiness. So let me take the most simple example. So here's an example of a subjective function. So what's a good search ranking, right? This is something that many companies worry about, right? And here's the first idea. This is about 40 years old. This is due to Gerald Salton from Cornell University. So what he said was, let's take every document that you're going to search and turn it into a vector in a space of all possible terms. So to give you a sense of that, all possible terms in the web is about a few hundred million, okay? So that's the size of the vector space. So in this vector space, you're casting all the documents. So every document becomes a point in this vector space, okay? And you can play games with exactly where you put these points depending on the presence or absence of terms, okay? And then along comes a query, which is also a vector in this vector space. And you say, well, the score is the dot product of the query and each document, and then you pick off the top scoring dot products, okay? So we then invest a lot of energy in computing these dot products efficiently in data structures for picking off the top 100 dot products given any query, okay? And you know, I assure you, this is not how ranking is done today. I'll get to that in a second. But this was sort of the genesis of modern search ranking about 40 years ago, okay? Okay. My point here is that a good search ranking is the kind of thing consumers are looking for, but it's very hard to write down a nice objective function of exactly what it means, okay? Let me give you some more examples, okay? People want beautiful pictures of sunsets, and you say, well, you know, how do I mathematically capture a sunset, or what's beautiful? You have questions like, I have several feeds from video cameras at a stadium, and I want the system to automatically determine the best view of each of these 6 cameras. So there's a selection problem there. Show me songs that I like. Okay, that's a prototypical problem you face on Amazon, Rhapsody, etc. Parenthetically, I've said spell correction. Spell correction turns out to be one of the few problems that in this realm of user happiness that we've actually done a pretty good job of mathematically characterizing. In simple terms, here's what we do. We look at the dictionary of possible words that you could type, whether in a document or in your phone or whatever, as a set of code words. And then we build a noisy channel model, which is often derived from empirical observations of how people actually type. And then it's a decoding problem. So you do a maximum likelihood estimate to figure out what the most likely word is that you're about to type or trying to type, right? So that has a relatively clean formulation, unlike these other ones that are far more nebulous. Okay? Right. So here are some characteristics of these subjective functions that we're trying to optimize, right? So the first thing is, how do we assess our algorithm? It's not like you can write down a runtime or write down a space bound or whatever. You end up, in some sense, asking users. So what does that mean? I'll show you in a couple of slides what it means to actually ask users. It's not the case, of course, that Amazon or Google goes and asks every consumer what they thought of a search ranking. But we do learn, and the key word that will keep coming up here is learn, from consumer behavior by watching what they click and where they go and where they spend their time. Okay? Now, here's a second crucial observation. Unlike the world of traditional algorithms, of SQL and so on, users have some tolerance for junk. Okay? In other words, absolute correctness, as heretical as this may seem, absolute correctness is not a prerequisite. If you get the wrong answer 5% of the time, it's okay, as long as there isn't somebody else out there getting it wrong only 2% of the time, right? And when I started working in search, it took me a while to understand this, that people are okay. They don't expect perfection, and that's a characteristic of the consumer world. Their experiences are so shaped by other bad experiences, by anticipation of things that don't work. You really have to get your error rates down to a point where they stop noticing, okay, where they stop going into parties and talking about it. Okay? Here's the point that Christos was alluding to when he opened his remarks. In many of these situations, infinite computing really doesn't help, right? We are not resource bound to a first order. And you know, the challenge that I always pose to people is, if we get a solution that demands lots and lots of computing, we're in great shape, because as algorithm designers, that's when we know how to bring it back down. That's our realm, okay? So bring it to our domain, to our competence, where resources become the primary consideration. Okay? And the issue is, in many of these problems, resources are not the primary constraint. Right. So how do we attack these problems? Here's the generic approach that we use. And if you haven't seen this before, you may be a little shocked at how intellectually shallow it is, but this is how it works. Okay. Okay. So after Salton did his thing, for the next 25 years until the web came along, here's what happened, right? People worked hard on weighting the axes in the vector space to try and get better and better ranking. And essentially, the premise was that the people doing the searches weren't ordinary consumers. There were information scientists, experts, intelligence agents at the CIA and places like this who knew exactly how to formulate a query. They had a deep understanding of the collection of documents. And so this is a very, very artistic glass bubble setting that search ranking worked in. Okay? When the web came along, starting about 1995, there were sea changes in how we started thinking about search ranking. So the first thing is that, you know, I think of these as ordinary people with extraordinary expectations. They type 2 words and expect magic. And increasingly, with things like suggest, they type 2 characters and expect magic, right? And that's a demand, especially on mobile devices, right? The other thing that hit us with the web is adversarial content. The web is an ecosystem of 1 billion people, each with their own motivations. So not all of them are interested in giving you content that makes it easy to rank. Okay? All right, so what do we do? Okay? So let's take a simple example. Let's say you're back in 1995. This story is actually 1998. You've been doing cosine dot product ranking like I had several slides ago. And along comes a student and says, you know, I have a new way of scoring documents. It's called PageRank. Right? So what do? Well, you say, OK, I got PageRank. I got this other traditional score. I got to combine them in some fashion. Okay? And the problem you're left with is combining these in a way that makes users happy. Okay? And one way to do that is to set that up as a regression problem, okay? Where you say, well, let's postulate that what we need is a linear combination of these. And then the way we're going to discover the best linear combination is to regress it to users' explicitly or implicitly expressed judgments. So we'll see where people click. We'll see where people abandon searches, and try as best as possible to retrofit the implicit signals of user behavior. Okay? So now, I said a couple of slides ago that this is where machine learning starts to get in. And really, that is the state of what we do today in these subjective function problems. So whether it's good search ranking or likable songs or whatever, what we're doing is really we reduce the problem to machine learning. We stop trying to understand exactly what the objective function is. Okay? We presume a machine learning kernel somewhere, which is at its core a large math programming formulation where you're trying to minimize some loss function. And so what does an algorithm designer end up doing in this world? Well, the first thing is you invent new signals. So you come and say, well, I invented PageRank. This other person invented a new signal for detecting spam or whatever. And then hope that you get lots and lots of data from users to train the machine learning. And out pops a ranking function. Okay? There's no real explanation for why it's 0.6 times PageRank plus 0.4 times cosine or whatever thing, right? So this is a very strange world to be in. And now I don't want to minimize some of this, because inventing new features often entails fairly sophisticated understanding of how users behave and fairly non-trivial computations in themselves, algorithmic computations. But in some sense, algorithm design in this world has been abdicated to machine learning, right? And you know, again, if you find this a little heretical, it's the state of how we're solving most problems today in the consumer world, which is we are optimizing functions we cannot even cleanly describe, right? And from an operational methodology, what we do is we come up with a strawman solution, then we get more data, and we iteratively improve and improve and improve. And this has become a standard methodology. Unless you think it's some hack in industry, there's actually lots of very competitive computer science conferences where 90% of the papers are actually in this realm. Okay? Data volume turns out to be paramount. Some of you may have heard a talk by my colleague Peter Norvig, who gives you all these examples from machine translation, spell correction, that basically say the way you win in this game is to just have more data. Okay? But the thing that in some sense struck me the most is algorithm designers, people like myself, have stopped looking at the RAM or the Turing machine as an abstraction. We instead presume this machine learning kernel and say, okay, what can we throw as by way of features? And this is a new world, which really has been brought about by the fact that we're not able to cleanly characterize and succinctly characterize what consumers want. Okay? All right. My last slide on this has to do with notions we can now attack with these methods, so ending on a bit more of a positive light, where we can start to get to strawman notions of even some vestiges of aesthetics, right? So I could ask a question, which of these web pages is more appealing? And these are experiments we've done, where you take 2 bitmaps and present it to a machine learning algorithm, and based on user feedback, you can start to say, well, this is actually more aesthetically appealing. Okay? John Kleinberg has done work where he says what phrases are memorable slogans. Okay? Again, using the same kinds of methodology, right? And then you can go back and try to see what would be nice is to bring back to the theory of perception and to linguistics. What is it that makes a phrase memorable? What is it that makes a picture beautiful, memorable, right? And we can do a decent job on these problems without any pretense of actually understanding aesthetics, right? And certainly not of synthesizing creativity. You can say, well, the way I'm going to try and produce a beautiful page is create 16 designs and pick the best of them, right? This is not to say that we necessarily. So the point is, we're in this funny phase here where many of the things we think of as somehow innately human can be machine learned. And for those of you who have got a background in machine learning, it's often the case that once you've set up the feature spaces, the decision surfaces that you use are relatively low degree, right? It's not like you're doing something incredibly fancy. Often very low degree decision surfaces can give you a decent job. So this is this puzzling world where we're not able to characterize these functions we're trying to learn, and yet we do a decent job using fairly simplistic, by some measures, machine learning. All right, so that's what I had to say on this theme, the first theme of subjective functions, this world where we're attacking these consumer-driven computations, but through machinery that we didn't learn in graduate school. This is not divide and conquer in dynamic programming and math programming, which is sort of the sequence that we're all taught in algorithm design. It's, figure out the features and let somebody else do the hard work. And the machine learning kernel will write down the algorithm. Okay? Right. The second theme I'm going to talk about has to do with the data that arises in consumer-driven computations. Okay? And those of you who've seen the phrase fat tails before, probably familiar with some of what I'm going to talk about. The setting that you should probably think about is graphs like the web, like friendship graphs, that have low average degree, but then there's a fair number of degrees, nodes with massive degrees. Okay? Okay, so the term long tail, which is a misnomer, was coined by Chris Anderson about 10 years ago. He was the editor of Wired magazine. And he would produce pictures like this, where he would say, well, the reason Amazon is going to beat Walmart is Walmart can only store 40,000 products in its store, whereas Amazon can sell 1 million. Okay, so, and therefore, and furthermore, he argued that mass in the tail was pretty huge, and so Amazon would therefore make a lot more revenue than Walmart. And the same thesis was applied to books, to music, et cetera. Okay? So Netflix and Blockbuster, et cetera. Okay? So he postulated this notion of infinite inventory stores, which in some sense get replicated also in the graphs that we deal with, right? So most products are misses. Not too many people want them. But in aggregate, these worst sellers account for a large fraction of sales, okay? And then he produced impressive statistics. And in the business world, this has been somewhat received with mixed reactions. And in fact, following Anderson's initial work, we and others have done a ton of investigation into the detail of data, some of which I'll share with you, that on what's really going on here. Okay. All right. So the first question I want to look at is, could the world be bimodal? So maybe there's nothing special about these heavy tails. Maybe what is really going on is that if you look at the matrix of people and their interests, okay, the movies they watch, the books they purchase, etc., right? There's really two distinct populations. There's normal people who read USA Today and shop at Walmart and Target and so on. And then there's the weirdos who watch the Bergman movies and go to very specialty stores and so on. So one of the things that emerges when you look at a lot of data from movie popularity, from search queries and so on, is in fact, this is not the real world. The real world turns out to be much more homogeneous. We are all partially eclectic. So suddenly we turn from weirdos to eclectic, right? So interestingly, every one of us spends a lot of time in the normal zone, in the head zone, but we all make forays into the tail. And if you want more details on this, there's a paper from 2009 by Broder et al. That actually details the study, okay? So in other words, the world doesn't partition into two normal distributions or a small number of normal distributions. There is something more going on here, okay? Let's look at some more data, right? So here's a picture that began emerging about 15 years ago. A number of groups, including our group at IBM, made this observation. Forget the fact there's two lines, they're red and blue. They're saying basically the same thing. So I asked the question, look at the in degrees of web pages. How is this distributed? Okay. So I want to draw your attention to the fact that this picture is log-log. So on both the x and the y-axis, the degrees are plotted logarithmically. And the fact that you get a straight line, you can essentially infer something that looks like this. You're getting like roughly an inverse square law on degrees. Okay. Now that is a fat tail distribution, as you can think. It's not a binomial or something like that. Okay. And it's not the kind of thing you would expect in an Erdős-Renyi random graph. All right. All right. So what are these heavy tails? So we're looking at probability distributions over the integers. And what we're saying is you pick any big number, the tail mass remains non-trivial. And that's what Chris Anderson talked about and all these pictures have said. Okay? Now, the striking thing, and this phenomenon, Michael Mitzenmacher has a beautiful survey that points out this phenomenon has been observed for almost 150 years now. But in a number of settings, it's the population of cities, income distributions, the popularity of movies, the number of friends you have, you keep seeing these distributions. So consumer behavior recurrently brings up these phenomena. Okay? So I showed you that in degrees, for instance, follow this so-called power law. Okay? And if you want a lot more detail on these distributions, I would urge you to go look at Michael's survey. Okay? It's a misnomer to call them long-tail distributions, although that's what most of the public calls it, because the interesting thing is not that the tail is long. The interesting thing is that there's a lot of probability mass in the tail. Okay? All right. So let's say we would try and say, if Erdős and Renyi don't explain what's going on here, if we had to postulate how these come up, I'm going to show you an explanation, okay, which is a fairly popular explanation. But what's interesting about this explanation is it's also borne out in a lot of web behavior, and I'll point that out at the end of the slide. Okay? So again, if you think of edges arriving in sequence in a typical random graph model, there's a parameter, I'll call it alpha, and it tells you the probability that you come in and link to a random web page. And with probability 1 minus alpha, you copy an existing link. So what does it mean to copy an existing link? You choose a web page in proportion to its existing degree. It's equivalent. Think of you're writing a paper, you're looking at citations. You see somebody else's paper, and you copy some of the citations over. Okay? That's essentially the process we're mimicking here. Okay? Now, what's interesting is that on many news sites on the web, Yahoo, CNN, etc., this actually is exactly the process that's going on. Right? They use something called explore exploit, where some of the time they're showing you popular news stories, and then some other times they're showing you a random news story just to assess the public popularity of this unknown random news story. Okay? So explore exploit, in the simplest form, essentially is driving these processes. Okay, so what happens if you run a process like this? You can write a difference equation that tells you how the degrees evolve. But what pops out is that you can solve this and show by a bounded difference argument that indeed the degrees follow a power law. Okay, so all right. So that's a start. And this analysis is pretty old by now. And there have been improvements over time. Some colleagues at Microsoft actually took this further and tweaked the models to better fit the web and so on. So there's a case where some understanding of human behavior does match some observations of web-like graphs. Okay? Right. So the first thing I want to point out here is for those of us who've been doing probabilistic analysis of algorithms, this opens up a new chapter. So consumer phenomena yield these heavy tails. Okay? But most probabilistic analysis we've done historically uses light-tailed distributions because we use simple generative models for random graphs that say, well, let's throw in an edge at random and throw in another edge at random and so on. And then we have the superposition of independent events. And the typical way you do this is to say bad things seldom happen, right? With fat tails, bad things do happen more often than seldom. And that's the challenge here, right? So the work ahead here, the first step is to try and analyze data structures that we use in algorithms under heavy-tailed inputs. And we've done some preliminary work on inverted indexes and graph compression, which are the problems that arise in practice and industry. But I would actually say we really should be looking at all the probabilistic analysis we've been doing and rerun them with these heavy-tailed distributions. Not necessarily because industry is going to use them, but I think in the process we're going to discover new mathematical tools that will help us move the field forward. A step further, what this demands is, well, I gave you a very simple generative model and argued that it has some vestiges of human behavior. In fact, you should be able to do better modeling analysis of the underlying human behavior. And this is a theme I want to pick up from here to the end of the talk. We really should be trying to understand what it is that motivates users to behave the way they do, and then try to capture them in relatively simple and clean generative models. Okay? We've already observed that the behavior of users, of consumers, is correlated to each other. When I copy somebody else's behavior, when I go ask 4 friends, which phone did you buy, and then buy the same thing, I'm copying behavior. Okay? So definitely, there's correlation between users, but there's also correlations that arise from what I'll call market forces. And I put this in quotes because it's not the full weight of market forces in the sense that Al Roth will talk about in a few minutes. Okay? But let's just take the simple setting. You go to Amazon or wherever, and it says, you know, people like you bought these products. Okay? So you're influenced by that. Okay? So there's a graph of people and products, and you get a recommendation that's pushed in your face. Now you're thinking it's reshaped. Okay? What does that do to the distributions you observe? Okay, do you still get these fat-tailed distributions? We don't quite have the analytical tools to understand this, right? And in fact, a lot of things that are somehow external to your own behavior start to influence your behavior. Of particular interest is something that journalists have started calling the filter bubble. If you look for filter bubble on the web, you'll see a number of articles that say things like, the internet is making us dumb because a few companies like Google and Yahoo decide what it is we see, and they hide everything else from us. Okay? Now, presumably when editors at a major newspaper or magazine decide what you see, that's okay, but if a web company does it, it's not. So the filter bubble is this name they've given to the fact that somehow most of the good stuff is obscured from you because web companies have decided you shouldn't see anything else. And what would be interesting here is to build plausible models of behavior as affected by recommendation systems, and then try and argue that, no, well, Yes, there is a filter bubble, or no, there isn't. And that would be a nice observation, a sequence of observations on human behavior. Okay, the last segment of my talk today switches to parallelism. Many of you probably heard this misattributed quote to Thomas Watson Sr., the founder of IBM, that the world maybe had a market of 6 computers. This was supposedly in the early 50s. I traced it back, and the nearest person I could find saying any such thing was Howard Aiken, actually. And in a strange way, I would say we're almost in this world of 6 computers today. Okay? And you say, what do you mean? I have 3 computers in my backpack. But there is a sense in which there's 6 or 10 or maybe 20 computers in the world today, which is the clouds operated by the major service companies, whether it's IBM or Microsoft or Google or whatever. And really what you're carrying in your backpack is a display device. Okay? And so this has sort of transformed our thinking in terms of what is it we do with this cloud? We have these thousands, hundreds of thousands, millions of machines. And this seems like a dream come true for PRAM designers, except it didn't quite pan out that way, right? So for those of you who are old enough, you'll remember these things called PRAMs. We all designed algorithms for them. So it was a nice, simple abstraction. We had shared memory, very fine-grained computation. Things were very synchronous. The world moved in lockstep. Machines never died. And in principle, programming was very straightforward. Okay? And then some of us, certainly myself, we went off and started looking at networks of fixed topology. We said, well, nobody can really build a PRAM, but we can build a hypercube or a cube-connected cycle or something like this. And then we started designing these very elaborate and, in retrospect, very brittle algorithms for making use of them, right? We never thought about what happens if one node of a hypercube dies. Presumably, everything dies, right? Les Valiant told me it's more than 20 years since he proposed the bulk synchronous parallel model, BSP. I didn't realize it was quite that long ago. But Les's model was really a forerunner of what we end up using today, right? In the reality of today, we have fault-prone processes. By the time you assemble a cloud with 1 million processes, a few are going to die every hour, right? Synchrony is coarse-grained. There is no notion of lockstep. There's no notion of a global clock that keeps all your machines in sync. In fact, some of them will occasionally time out for this reason or that. Okay? Locality of data access does matter. Okay? And here's the killer that most of us didn't really realize, that you may pay $1,000 for a machine, but then you pay $100,000 maintaining it. I mean, that ratio seems a little off. But certainly software development and maintenance costs far dominate the cost of hardware. And so in some sense, what we want are paradigms for amortizing that over a huge number of machines and keeping the programming abstractions very, very simple. Okay? Now, in our realm, in the consumer realm, we want to solve problems such as which search queries co-occur, or which friends to recommend, or which products, or whatever, right? And so I want you to keep that in mind as I go through the next few slides on the reality of parallelism, right? One other thing, I made this comment on software development being a killer, which is a little hard for us to model and abstract in theory. But the standard solution, if you had something like a PRAM, would be to use threaded programs. And if any of you has done any threaded programming, it's a nightmare to actually debug and run these things. Okay. The next couple of slides I've borrowed from Sergei Vasilevitsky, my colleague, who, with some other colleagues, has actually been trying to build something of a theory for these MapReduce style computations. So MapReduce is a paradigm for parallel programming that has come to dominate the way we do consumer parallel computation in the real world. Okay? The way to think about it is a lot of the hard work of keeping machines alive, checking who's dead, moving jobs around, is left to an underlying library in the cloud that's taking care of all of this. And as a programmer, all you have to do is specify 2 functions called map and reduce, and I'll explain their roles in a second. Okay? So all the stuff about data distribution, synchronization, et cetera, is left to the MapReduce runtime system. But in turn, this restricts you to a certain stylized view of parallel computing. You don't have arbitrary PRAM power. Okay? certain kinds of parallelism are allowed. And one of the things that is just starting off, and I want to point to as a rich area for further work, is to build a stronger theoretical foundation for these MapReduce styles of computation. Okay? All right, so a couple of basics. So you look at all data in key-value pairs. So that's the only way you're going to manipulate data in MapReduce. Okay? So for instance, a graph, you think of it as a list of edges where the keys are the edge names and the values are the weights. Okay? And essentially, you have three, really, map and reduce are the primary two programmer's view steps. Okay? So the map function essentially takes a key-value pair and then, with shuffle, aggregates all the pairs of the same keys. So all attributes of a given edge are sent into one bucket. Okay? Here's another example. You can say you have a bunch of documents, you're parsing them. Then you can say that I want to map together all documents or document IDs that contain a particular word. Okay? This is a routine step in constructing a search engine. Okay? And then in the reduce phase, you can do things like, well, now that I've gathered all the document IDs containing a given term, given word, into one processor, I can sort them out to create an inverted index, for instance. Okay? So the map phase distributes the data around to reducers, as they're called, and the reducers then finish up the work. Okay? Now, between these distribution steps, there's a lot of local computation going on. So I don't want you to think of this as one clock cycle. There's lots of clock cycles going on, and then one distribution step, and then a reduction step. Okay? And so the environments one deals with, you have tens, could be tens of thousands. This is not just, you don't have to work at Google to do this. If you're an academic, many academics I know do this using, for instance, Amazon's cloud services. Okay? Right, now even if you have a terabyte-sized data set, your machines, your basic nodes, only have about gigabytes of memory, so forget trying to get all the data into memory. This is good for batch processing, so it's not something that you do for serving queries, for instance. It's really something you do offline. Okay? Now, if it helps you think about it, and this is not material to what I'm about to say next, right? Think of sublinear memory per machine and a number of machines that's sublinear in the input size. Okay? So computation proceeds in these map-reduce rounds, and typically you're looking for a constant number of rounds, but within a round, a lot of stuff goes on. Okay? All right, so I'm going to give you a simple example of how you might try to do something we want to do a lot. If you have a social graph, for instance, you want to do things like count triangles. Okay? And then show you how things can go bad here because of the data distributions that arise in practice, because of fat tails, and then how a simple fix fixes it. Okay? So if you want to count triangles in a graph, what you do, one way of doing it sequentially, is each node looks at its neighborhood and then tries to count up the triangles it's involved in. And the runtime, in this case, every triangle gets counted 3 times, is the sum of the degree squared. Okay? And in practice, this will be quadratic because of these heavy tails. Some vertices will have very high degree. Okay? All right, so here's a naive parallel version. You generate all possible path 2 pairs. So here I am, I'm sitting here. I look at my 2 neighbors. Okay? Send all these paths that include me in the middle to a reducer that then checks if a triangle can be completed, and then sum up. Okay? The problem with this is that the fat tails strike again, because the reducer that takes the high degree node in the middle takes forever to complete. So one of the things you observe when you run these things is the first few reducers finish really fast. 90% of the work is done in a few minutes, and then the whole thing can take 20 hours. Okay? So you see why fat tails hit us again here. Okay? And I've given you some representative numbers here. So data skew, in particular the fat tail, defeats naive parallelization. Now here's a very trivial modification of that algorithm that suddenly turns out to magically work. Right? So instead of counting each triangle 3 times, just make the lowest degree vertex in each triangle count the triangle, and the others ignore it. Okay? That seems like a trivial modification, should only save a factor of 3. In fact, it wins. Okay? So why does it work? Well, let's partition our nodes into 2 groups, the high nodes and the low nodes. The high nodes are the ones with large degree, bigger than square root of m, where m is the number of edges. Okay? There's not that many of them. Okay? And the crucial observation is there are only about m of these paths where a high node is in the middle, right? Because you look at my neighborhood, right? The total number of high nodes is only about root n, right? Okay, so the total number of paths from high nodes is m to the 3 halves. For the low nodes, it's you sum I squared times ni. You can show that to be m to the 3 halves again. So the total work is m to the 3 halves, which is the best you can do. But what about parallel runtime? Okay, what's neat here is the algorithm, when you do it this way, automatically load balances because it only sends things to the lower degree nodes in each triangle. And as a result, the maximum number of paths any reducer has to check is m. Okay? And so instead of taking 27 hours, everybody's done in 5 minutes. Okay? So fat tails get tamed by this seemingly trivial modification. And the reason I want to stress this is, again, my earlier point, when you're doing parallel computation in this realm, think about the data distribution, and that shapes how you think about algorithms. Okay? And the per round runtimes come down dramatically. Okay, so let me just finish with some closing thoughts, right? So as I said, ordinary users consume a growing share of computation, cycles, storage, etc. And their expectations reshape the computational problems we pursue, right? So when I spoke of problems like, give me songs I like, that's not a problem I found in Gary and Johnson, right? But that's a problem we have to solve, right? The behavior of users, and this is sort of the really subtle part that I think will take us years to figure out, reshapes the data distributions we observe. I gave you very superficial explanations for how copying-like behavior gives fat tails, but that's just the tip of the iceberg, right? We really need to get deeper into understanding this. And this recasts how we think about and teach algorithms. Certainly, we have to learn all the classic paradigms. But now in this new world, I think algorithmic thinking has to undergo an evolution. Okay? I think this comes with tremendous challenges and benefits to computer science, and perhaps to the social sciences more importantly. One of the things that we're constantly hampered by in our industry is we don't have people who understand user behavior and large data and algorithms, right? So the caricature I have is we don't have psychologists who can write MapReduce programs, right? And really, if you go past the caricature, I think the opportunity here is for us to start to understand human behavior on a scale that we never used to before, because your typical social science experiment involves tens of people. But at the same time, so you have the scale of computer science coming in, the machines and so on. But hopefully with the depth of thinking that social scientists have dedicated hundreds of years to, I'm certainly not qualified to think hard about exactly how human behavior works out. So I think combining these two should create really fertile directions. And it certainly behooves institutions like the Simons to promote this kind of work on campus, and I hope to see a lot more of it because it will benefit us all. Thank you.
Questions for Prabhakar?
Josh.
If you think about training using machine learning on the sort of granularity of the individual person and not as a whole of how we all collectively behave, is there enough data to do that to be driven by what people want and the dynamism of how that's changing for an individual?
Yeah, so Josh's question was, would the data be too sparse to train on individuals, right? So what we end up doing is we sort of have global models that describe population as a whole. Then we have segments that implicitly or explicitly correspond to recognizable segments, like teens versus elderly, retired versus whoever, right? And then sometimes you go further down by saying, okay, this person really seems to like both philosophy and computer science or whatever. And you tune to that. So it's really a hierarchy. And at the higher levels, obviously, you have more data and have more confidence. And the danger of overfitting with sparse data, of course, is you bug users who say, well, my grandson borrowed my iPhone and did a query, and now I'm getting inundated with whatever, teen pop or something. Right? Yeah.
generation of features is a very important aspect of the overall effort. Could you comment on the possibility of not capturing consumer behavior models of behavior in the sense of if we looked at, say, physical situation and said, well, we're going to model balls falling off of many towers, and we'll throw in color and we'll throw in is it air particle?
Right.
And then we'll
Okay, so you're setting me up here, right? Because so the question was, well, what if Galileo had access to machine learning and he, threw in the color of the balls he was tossing from the leaning tower as a feature? Could he get all confused? Yeah, I was at a meeting in Washington, D.C. when someone came along and suggested that we should forget climate science and instead replace it by a machine learning model that just took the last 2 years of weather and tried to predict tomorrow's weather. Now, that would be a mistake, because if you have hundreds of years of understanding, that's always preferable to a new feature, right? The trouble in many of these situations is we don't have a lot of understanding for the reasons I said. We don't have deep social science understanding. And second, the consumer world is not stationary in the stochastic sense. It keeps evolving. So yesterday's models don't necessarily work well next year, right? And for that reason, we don't always have time to settle down with sound understanding of consumer behavior and realize that the color of the clothes somebody is wearing isn't a good feature, right? And so it is true that we probably place too much emphasis on the power of the model and not enough on understanding. And part of my appeal here is let's try and put more wood behind the underlying behavior before we get too caught up in this. But this is all we have for now. Yeah.
So you ended your talk with a thought on the grand challenge in the day-to-day of understanding human behavior on a scale that never before possible. I humbly suggest that our challenge is, in fact, to understand the behavior of life on Earth, not just humans, at this time.
Okay. I think that's a very fair comment. It's probably the case we'll begin first with humans, but there are certainly, in his talk, John Kleinberg didn't talk about non-human behavior, but there's people in this field, broad field of so-called network science, that are actually looking at food chains and other aspects of networks. So I'd say we are still scratching the surface, and it's very wide open at this point. Yeah.
We talked about the difference in the filter bubble and the New York Times, and I was wondering if maybe the difference has to do with people's understanding. So first of all, everybody understands that the New York Times has an editorial board, but when they search, they think they're in a sort of informational comments, and if they don't understand that they might have been receiving personalized responses, they have no idea that they're missing something, let alone what it is that they're missing.
Right. I think what Cynthia is pointing out is that there's different forms of trust engendered by the New York Times versus, say, Google or Bing or somebody, right? The New York Times has a storied history of trustworthy reporting and editorial culling, and people have grown to depend on that as a definitive source of truth. With search engines, it's a little more random for sure. There's this black box that.
I may not even realize that I'm just getting the liberal view.
That you're just getting, sorry?
The liberal view, because they're personalizing based on my history.
Yep. Yep. Whereas you're saying that when you elect to buy the New York Times, you've elected to get the liberal.
But I understand where it is.
That's right. So that's a path that, frankly, we have to tread on very carefully. The degree of personalization that you're talking about, the liberal view for a search engine, is, I think, at the point of being technical feasible, but we're all sort of skittish about doing anything like that, simply because of the concerns it'll raise amongst the people who understand, as opposed to the people you're talking about who may not even realize that they're being liberal in the process.
Well, the objection is you are doing it without even realizing you're doing it, because you're giving her liberal web pages.
Well,
because of her search history.
Well, so we're not trying to do that, as far as I know. Yeah. Yeah.
To continue along this line, could you presumably cluster viewpoints and then build, get the top 3 or something, and then build in buttons that you can click and then say, oh, show me the Republican.
Yeah.
Search results. Show me the liberal.
Yeah. So here's something that some years ago we did as an April Fool's joke when I was at Yahoo. We put up a search bar, and there was a red button on the right with an elephant and a blue button on the left with a donkey. And you could click either, and you'd either get blue links or red links. And it was an April Fool's joke, and it was done as a complete hack. But people took it very seriously and got really upset, right? And so it's not something that I think any search engine would do lightly, but technically what you're saying is feasible.
I have a question. You mentioned that a challenge for algorithm analysis is to analyze algorithms under these new distributions. Would it be more interesting and more scientific if instead of taking the distributions, go to the organic generated models and try to analyze algorithms for generated models?
Implicitly, that's what you want to do, because eventually when you do the analysis, you're not presuming the distribution, you're going to the underlying generative models. That's how you end up doing the analysis. So yeah, that's absolutely what you do. Now you have to believe in the generative model. Beyond, yeah, it seems to produce the right distribution, and that to me is a leap of faith.
Sure.
Jitendra.
Again, picking on this data bias issue,
Yeah.
I mean, I think there is this peculiar, I have this worry about this solipsistic self-reference getting out of hand.
Sure.
So to give an example, computer vision systems are being trained with images that have been retrieved from Google search.
Yep.
And so there were certain kinds of images on which those systems worked and were retrieved because recall is always lower, precision is good. And now we have become happy because we can do well at that. Of course, there is this entire dark matter that we are ignoring.
So Jitendra's objection is that computer vision is trained on images obtained from an image search engine on the web, right? And is that good science? And of course, it's not good science. But on the other hand, you compare it with the bulk of what's happened in the social sciences. I don't know how many of you have read the recent discussion on so-called weird people. Anybody heard of weird people? So weird is this acronym that stands for Western Educated Industrialized something something. And essentially, it points out that most social science research is done on undergraduates in North America. Okay. So is that a bias? Yeah, I would argue that's a bias, and hopefully not as frightening as. So we're taking steps in the right direction. I would agree we're not all the way there.
Okay. Thank you very much.
Thanks.